Hello everyone, welcome to this webinar on 3DI results analysis. My name is Jonas van Schooijenstein Landman and I'm the product manager of Nederlands Humans Technologies. Welcome Leendert, can you shortly introduce yourself?
Yes, my name is Leendert van Wolfswinkel. I'm product owner for 3DI and responsible for product development in that capacity. I'm really happy to be able to showcase 3DI results analysis today.
Okay, thank you. As I understand it, in this webinar, we don't have a presentation, but we are going to show you the tooling and how it works. First of all, Leendert, why is it important? What is the main goal actually of the 3DI results analysis?
Yeah, the main goal is to get insights from the simulations that you have done. I think that the results that you get from a simulation, there's a lot of information in it, but to make it accessible also for non-experts and to really get an understanding of the water system from all this data that 3DI produces, yeah, it really helps to know your tools.
Okay, and what were the main goals when developing the 3DI result analysis tool?
Yeah, I think the main goal was to make it as easy as possible to get these insights. I think especially when you use integral models that have 2D components, 1D components, the complexity of the model increases. And yeah, we really designed 3DI results analysis to make analyzing these simulations as easy as possible and to cut through this complexity. Yeah, we have seen that for our clients, comparing results is really important. So that has been a guiding principle throughout the development. Keeping the projects tidy, even if you have a lot of layers, a lot of data, and also consistency between the different tools, so that it's easy to use all the tools at the same time.
Okay, and maybe you can show it. Then how is it integrated in the rest of the workflow?
Yeah. I will share my screen to show that, and then I think after that I'll also immediately jump into the demonstration
all right.
of all the tools.
Thank you. Looking forward.
Okay. Yeah, so if we look at the 3DI modeler interface as you see on your screen, there are all the functionalities are integrated into this single interface. So here at the top we have everything that is needed to view schematizations and to edit them. Then here this button opens the models and simulations panel that takes care of everything for uploading and downloading everything that has to do with the API. And this toolbar is the 3DI results analysis toolbar, and another important location where you can find tools for analyzing results is in the processing toolbox, which you can open using this button. You'll find a lot of QGIS native processing algorithms, but also two categories with 3DI specific processing algorithms. And in the demo that I'll be giving, I will use both the tools that you see in this toolbar as well as some of the tools that you find here in the processing toolbox. I have chosen a demonstration model in Denmark. Perhaps if you attended the previous webinar, we used the same area. and this model is located in the town of Lango. We are going to analyze a pluvial flooding situation. It is a fictional situation, but I think it bears a lot of resemblance to the kind of analyses that are done often with 3DI. So what we have, what we know from the client is that in this area, this red area of interest, there are some houses that when it rains a lot, the inhabitants complain that there is flooding near their houses, in their gardens, or even in their houses. So yeah, let's start with just adding some more background information. So OpenStreetMap is of course always helpful. So I'll hide the model and the digital elevation model, and also a satellite image. So if you go to Quick Map Services and then search QMS, I often use this one, so I will add the Google satellite right here. Yeah, so this helps us understand a little bit better the situation. And we have done simulations with a model of this area for two rainfall events, 40 millimeters in 1 hour and 60 millimeters in 1 hour. So let's start by downloading those. So we go to the Models and Simulations panel, download results. And as you can see, we have this Langa model. There are two for the current situation. So I start by downloading this one. The 60 millimeters. And the other simulations are after taking some measures, which we'll get to later. Let's start by generating a maximum water depth map from the results that we have just downloaded. I think that gives a good indication of the severity of the problem. So in the toolbox, you go to post-process results and then maximum water depth. And it asks for the computational grid file, for the results file, and for the digital elevation model. So I go to my 3DI working directory for Langa. And then I see here the two results that I just downloaded. So let's make a water depth map for the 40 millimeter event. Let's just copy this path for the results file as well. So we have a grid administration file and a results NetCDF. Now we have to be really careful to select the right digital elevation model, because in this demonstration I will use two digital elevation models, one for the current situation and one that includes a new retention area. So I will use this one. Yeah, that's correct. And then I will make the interpolated water depth, maximum water depth. Okay. and I will save it to in this case I will save it to the same location as where the raw results are. So I call it maximum water depth. Yeah, and then I click run. To be a little bit patient, and what this algorithm does is it takes for each computational cell, it finds the maximum water level that occurs during the simulation. Then it interpolates spatially between those values to get a water level value for each pixel, and then it subtracts the digital elevation model so that you basically convert the water level values to water depth values. Okay. So now we have this raster file. I'll put it just above my schematization. And as you can see, it's all black and white, so it helps to style it. And I have defined a styling before, so I can apply this styling in every project. And this styles the water depth ranging from 0 to 30 centimeters. Okay. And we can see that in this area of interest, there is clearly quite a lot of flooding due to this 40 millimeter event. Well, most of the houses are still not flooded, but the gardens are definitely flooded, and I think there's also a risk for these houses. If you want to know the water depth, there's this tool called the value tool with this green button, and that will give you the water depth values for each pixel. So here, for example, it's about 40 centimeters of water depth. Here it's almost 60 centimeters. Well, I think the next step is to see how this water depth develops over time. And to do that, we will load the raw results using the results analysis tool. I click this button to open the 3DI results manager panel. If I click this plus button, I will get an overview of all the computational grids and simulation results that I have in my working directory. It is also possible to load results from any other place on your hard drive. Then you can use this browse tab. So if you downloaded stuff through another route, then you can also use them in the 3D modeler interface. Okay, I will double click the 40 millimeter event. You see that it adds the revision 21 computational grid for my Lambda model, and it has one simulation result attached to that computational grid. Let's also add the 60 millimeter event. So now we have these two events. Well, usually when you are comparing these results, it really helps to have short, distinctive names. So I will call this the current situation, and I use you can either double click or use F2 to change the name. I will call this 40 millimeters and this 60 millimeters. Okay. Yeah, and what I would really like to know before we can start finding a solution for this problem is where does this water come from? And I will use the Watershed tool for that. Okay. Yeah, at the top I can select the results from the ones that I have loaded in the results manager. I think for this case, the 40 millimeter event is regarded as the main event that there should not be any damage caused by flooding for this event. The 60 millimeter event is kind of a what if it gets even worse? So we will focus most of our analysis on the 40 millimeter event. I can change some settings. I will not go into those details. If you want to know exactly what these specific settings do, this is all included in the documentation, which we will also show at the end. The easiest way to use this tool is just to use the click on canvas option. I click on one of the nodes in the flooded area, and I have selected the upstream option, so it will tell me, okay, the flooding that occurs here comes from this area, and of course from rainfall that falls directly on this location. Another thing that is always interesting to understand is so now we know the spatial extent of where the water comes from. We will also want to understand how it develops over time. And for this, the time series plotter is a useful tool. So I click the pick nodes or cells and zoom in a little bit on the same node. And I will see two lines plotted in this graph. The one with the without the dashes is for the 40 millimeter event, and the 60 millimeter event is shown here. So what we can see here that is the first hour nothing happens because this simulation uses a dry period of 1 hour before it starts raining. Then during the rain event, the water level increases. There is a kind of maximum to it, and after the rain stops, it immediately starts reducing. Okay, so let's hide this for a moment. Okay, so now we know that the water comes from this area more or less, but we don't know the specific details of how it flows to this area yet. I will so in my 3DI results, I have my computational grid, and I also have a group of the outputs of this Watershed tool. Let's just hide them for a moment. If we go back to the results manager, we can visualize the results on the map canvas. It visualizes the net cumulative discharge in this case, and the water levels. For this specific case, I'm not interested in the water levels at the moment. So I'll go to the layer panel and hide those. So now we have the cumulative discharge at the end of the simulation. So here at the top, you see that the temporal controller has opened. And this temporal controller, it governs all layers that have a temporal component when in time the data is shown. And by showing the cumulative discharge at the end of the simulation, we get a good idea of how the total flows are. Let's just use a slightly different background. Also hide some of these. So we see that there's a lot of water flowing to this area. Then there's a road, and then quite a bit of water flows from this area here, crosses the road into our area of interest. So if we can somehow stop or buffer this water, that will probably reduce the flood problem quite a bit. There's also another way to visualize these flow patterns, which is when I am analyzing results, I really like these arrows because they basically exactly represent what 3DI has calculated. But for clients, it's if you want to make a map, it's usually better to use a slightly different tool. So if you go to the 3DI result aggregation tool, again, we select the result from the ones that we loaded. And in the list of presets, we select the flow pattern and we click OK. Yes, and then here in the layer panel, we see a new group called the result aggregation output. Then for the 40mm event, we have 2 layers of flow pattern. And let's just hide this group. And as you can see, this is a little bit more intuitive, although it's a further translation from the raw results. So if you are really a modeling specialist, the other type of visualization is probably more useful. And if you don't know a lot about modeling, but you want to know how water flows through your area, then this visualization is probably better. Okay, so let's go back to our solution. So the idea is to add some retention to this location. Well, of course, it helps to have a look at the satellite image. So we see that there is a kind of a shrub area here. So that it may also be promising. It may also be possible to add some retention here. But how much water should fit into this? Okay, let's so we will make a water balance for the area of interest using this tool. And the way it works is you need a polygon. In this case, we have our area of interest. You use the select polygon option, click on it, and it will start calculating the water balance. if we want to know how much water flows into this area, it's more useful to choose the cumulative water balance option. So we see that the total inflow in our area of interest is around 7,500 cubic meters, and also the outflow is close to 6,000 cubic meters. So this, and we see that this blue part is 2D flow, so that is flow over the surface. So yeah, what we basically see is that there's a lot of water flowing into the area, and most of it flows out also. If we look at the flow lines, we can see that this is the main flow route for the outflow, and there's a small bit of this green color, which is the rain that falls directly in this area. So we would need about 6,000 or 7,000 cubic meters of retention. Could probably also be a little bit less, but let's say that is a ballpark figure. And yeah, I have drawn this this polygon to lower this area by 3 meters. And let's see. So if I identify this. Okay. I can't find the identify panel at the moment, but what we can do is we label this area. We want to know the area, and we lower it by 3 meters. So we take the area times 3, and let's round that value for a better looking label. Yeah, so we have about 71,000 cubic meters of extra storage. So it's 10 times as much as what we need. So yeah, if we cannot use this whole area, we know that there are still some options. But what we want to know is, will this actually solve the problem? So I made a digital elevation model in which I burned this area, and I did additional simulations with that new model. So let's download those results as well. So we have the schematization that's called with measures, and we have a 40 millimeter and 60 millimeter event. Okay. And we add them to our results manager as well. So this is with 60 millimeters, and this is the 40 millimeters. And again, let's rename this so it becomes through all the tools a little bit easier to understand. So with retention, and this is the 60 millimeters, and this is 40 millimeters. Well, as you can see, automatically in the water balance tool, some tabs have been added. So with the retention, well, if we compare the water balance for the 40 millimeters with retention, then we see that the cumulative inflow is around 4,000 meters, and without measures it was almost 8,000. So yeah, the water balance really changed quite a lot. I have also made a different area of interest that includes just the area where the main flooding occurs. So we can also choose that area for our water balance. And it calculates the water balance for all 4 simulation results that were loaded. Now, if we look at this water balance for the flooded area, we see a huge difference, not only in terms of the total amount of inflow. So here it's only like 400 cubic meters left, while in the current situation it's 8,000. But also we see that 2/3 of the remaining inflow is rain on 2D. So yeah, even if we take more measures to reduce the surface flow, it won't help a lot because yeah, the remaining part is rainwater. Okay. Yeah, and of course we want to know what is the effect in terms of maximum water depth. I calculated these maximum water depth rasters before. Let's see, in the results, 40 millimeters maximum water depth. So let's rename this to maximum water depth with retention 40 millimeters, and put it here. Okay. Yeah, I will copy the style of the other maximum water depth and paste it so it looks the same. Let's also rename this to current situation 40 millimeters, and group them to keep our project tidy. Maximum water depth. Okay. Yeah, and if we use the value tool now, we can and we switch both layers on. Yeah, we can see the difference. So for this location, in the current situation, we have almost 65 centimeters of water depth, and in the yeah, with the retention, it is reduced to 27. Also, you can clearly see that the flood extent has changed quite a bit. So this is the flood extent for the situation with the retention, and this is what it was. So the situation has improved significantly. And if we look at, let's hide these results. Yeah, we see that there are still some locations where the flood water gets really close to the houses. But yeah, the flood depths have reduced a lot, and also the flood extent. Yeah, if you look at how it gets close to the house or further, our retention area has improved the situation quite a lot. Okay, so we know that this water, we also would like to get rid of this water, but we also know that most of it is rain that falls directly in this area. So we need to improve the drainage of this area, and what I did is let me see. Yeah, so I have added the schematization with revisions, with measures, like the second revision. That includes not only the retention basin, but also a pipe that drains this this area. Let's put it here. Yeah, and as you can see, the pipe runs through the back of the gardens and then takes the water to the river. And yeah, let's have a look at the maximum water depth map for this second option for measures. Revision 2, 40 millimeters maximum water depth. With retention and drainage. And we copy the style. We have a look. So with just the retention, we had this split extent, and yeah, if we also use this this new pipe, then yeah, it is reduced, but still there's quite a lot of yeah, flooding in the gardens remaining. Yeah, so somehow this pipe does not really work the way we want it to. So let's investigate why that is. First, of course, we will have to download the results. So we have this revision 2 of the schematization with measures. So we download this. And the 60 millimeters. And we will add those to our results manager, revision 2. 60 millimeters. Let's call this with retention. And 40 millimeters. Yeah, and we will analyze how this pipe functions by using the side view tool. That's the tool you see here. The way it works is I select the trajectory. Start point is the start of the new pipe. Wait, okay, sorry. The side view tool allows you to draw a trajectory for any of the computational grids that you added to your project. And of course, in this case, we want to do this for the last version. Sorry for the confusion. So I click on the start of this pipe. Then in yellow, I can see where I can go from this point through any part of the 1D network to end up in the river. So I click here. And what we see now is a side view of this situation. So we have a pipe that is pretty much flat, and the riverbed is also at the same elevation of 2 meters above sea level. And here we have the results that we can visualize. If we add the 40 millimeter result, then we see the water levels for the end of the simulation, because the temporal controller is set at the end. So let's move this to the start and press play. Then I can see how it develops over time. Well, at the beginning, the first hour, there's no rain. Here you can see the simulated time. Here you can see the real time. Let's pause it quickly here. So what we see is that even after half an hour of rain, this pipe, the gradients in this pipe are really strong. So apparently the 300 millimeters diameter of the pipe is not sufficient for the drainage that needs to pass through the discharge that has to pass through this pipe. If we move further, we see that it gets a little bit worse even. And of course, after the end of the rain event, the water levels lower again. We can also switch on both the 40 millimeter and 60 millimeter rainfall event. And we see more or less the same. We can draw the same conclusions, but obviously in the 60 millimeters event, it's just a little bit worse. I think that's those I think were the most important things I wanted to share. I did not show all the tools and definitely did not show all the different possibilities that these tools have, but I do hope that it gives a good impression of how you can use these tools in practice and how to combine the insights that the different tools give to really understand what's going on in your model.
All right, Leendert, thank you very much for this demonstration. Very interesting. For the listeners, if you have any questions, there is a question panel in your screen. Feel free to ask any questions that you might have at the moment. I have a few questions for you already, Leendert.
Okay.
The first one, if users want to know how to use these tools, where can they find more information except for, of course, this webinar?
Yes, let's go to the 3DI documentation. So docs.3di.live. At the left side, you see the user manual for the modeler interface. And the tools that we saw in the demonstration are all listed under analyzing results. And it follows more or less the same sequence as I did in this demo. It shows you how to download results, how to load them and visualize them, how to make these water depth and water level rasters, and all the tools that I showed. And yeah, each of these tools, for example, the results aggregation tool, it also explains all the different options that you have, what they mean, what they do, etc. So yeah, if you really want to get everything out of these tools, then definitely consult this documentation.
All right. Thank you. You showed also other tooling in the meantime. You showed the 3DI result analysis and the panel, but you were also talking about a value tool and some other tools. Are they also developed by Nederlands Humans, or are they installed in the model interface? How does that work?
Yeah, so the value tool, but also, for example, the profile tool or this quick map services that you can use to add satellite imagery or background maps. There are plugins developed by other like third-party plugins, but they are included in the 3DI modeler interface when you install it. So yeah, they are definitely available and yeah, super useful when combined with 3DI specific tools.
Check. And regards to that, oh wait, at the beginning you said I have to select the correct dam. Can you maybe elaborate a bit on what would happen if you select the wrong dam, for example, digital elevation model?
Yeah.
Why is it not used directly from the model, for example?
Yeah, so if you look at this map, you see these black computational cells, and what 3DI calculates is for each time step a water level for each cell. But within one cell, the water level is assumed to be the same. So you, yeah, in the raw results for a specific time step, you will find only one value for the entire cell. Well, if you look at the water depth map, you see that there's a different value for each pixel, and these pixels are way smaller than the computational grid. So what the tool does is to take this value for the water level in this cell and also for this cell, and then interpolate between these cells to get a water level for each pixel. But then the last step is to subtract the value of the digital elevation model, so you know, yeah, the depth of water. But if you use the wrong digital elevation model, of course you get wrong values for this water depth. Yeah, the tool allows you to play with this a little bit, so you can also use this to yeah, make a very quick estimate of what would happen if you make changes to the digital elevation model. But in general, I would really advise to always use the digital elevation model that was used to make these results in the first place.
Of course. Okay. I have a question here. How did you burn the area? I think you drew a polygon and then you said I burned it.
Yeah.
Can you maybe elaborate a little bit on what you did, what that means?
Yeah, I think the easiest is just to show how it's done. So let's have a look here. So we have the schematization rasters. So the original digital elevation model. Copy. Okay, so this is no. It's
already burned, I guess.
Already
but it just doesn't matter if you just show the tooling that you use, then I think that's sufficient for now.
Okay. Yeah. So this is the original one. So the original. Yeah, I go to the processing toolbox. There's this category called the GDAL, and yeah, I always forget the subcategory, so I will just type it here. Yeah, so we have three algorithms that are called rasterize, and in this case, we want to burn the same value throughout the entire polygon. So let's put this here on top. Yeah, so we select this algorithm. Yeah, the input vector layer is the lowered area polygon, so that's correct. The input raster layer is the original DEM, and it will burn it directly into the file. So if you want to keep the original file, please make a copy first. Yeah, and here we can burn, for example, -2 meters below sea level, and then just click run.
Yeah, or you take the value from the polygon, I guess.
Yes, another option is to use the override with attribute. So if you have multiple polygons with a separate value for each polygon, then you can use this tool.
Yeah, okay, and but you say you have to make a copy of the raster, but of course the raster file is also, once you have committed it to the 3DI servers, then you can always get it back from there, right?
Exactly. Yes.
Yeah. So then the backup is basically already your previous revision.
Yeah.
Other question is there infiltration in this specific example that you showed? Like I guess an infiltration raster or something?
There's no spatially varying infiltration. The only so if we look at the schematization, we have only a digital elevation model. I honestly don't know if it has a global value, and apparently not. So there is not no infiltration defined in this model.
Okay. And
yeah.
No, that's okay. It's just a curiosity. And you showed the sewer system that was going directly to the river. Isn't there also a chance of the river flowing back into in the sewer system and then causing a flood or something like that? Or is there like a, how do you say that? Like a one-way, like
a kind of
valve
flap gate or something like that. No, I did not schematize any gate or any structure. I think it's a very good question. But if you look at the side view, you see that even at this point, the water level in the river is here, and the entrance of the pipe is still like 40 centimeters above that. It does not occur in this case.
Okay. That's all the questions I see for now and that I have. Also myself. Is there anything else you would like to just highlight as a last thing that you say, okay, this is really something that I maybe forgot to mention?
Yeah, there is. There's one tool that I skipped, which is also interesting. So I have drawn these lines around the area of interest, and the tool that I want to show. Sorry. We have developed a tool that will calculate how much discharge passes over each of these lines. It can be found in the processing toolbox. It's called cross-sectional discharge. Again, you need to select the grid admin file and the results file, and the layer that you want to use for these cross-sectional. Yeah, there's a lot of other options which you can ignore for the moment. And then it will calculate the net discharge, the total net discharge that passes over each of these lines. So for the first line, it's 6,000 cubic meters, etc. And it also takes into account if water flows the other direction, it's subtracted from this value. So it's really a net value and not.
How do you read the minus and the positive in this?
Yeah, so it's
oh, it's already, sorry. Yeah.
It depends on the drawing direction of this line. So yeah, the left side, if it flows from left to right, then it's positive. If it flows from right to left, it's negative. But it depends on how you draw these lines. But the visualization helps to understand the result. Yeah, and this tool can also be super useful in this case to estimate the needed capacity for this retention basin.
Cool, looks really nice. Okay, I guess that's it, right? More to be found in the documentation. If you have any questions later to us, like how do you analyze this or that, let us know. And yeah, if we, oh wait, there's one more question coming in. Perhaps we can.
We have 2 minutes.
We have 2 minutes. When you add the retention area, did you make any connection to the 1D network? It's the final question. Other questions we will answer in a follow-up email.
No, at this specific location, there is no 1D, but yeah, water can flow from the 1D network into the 2D and from the 2D into the 1D. So yeah, there's no specific action needed to integrate it. It's already an integral model. So.
Yeah, I guess it's also based on after the rainfall event, what happens to the water that's standing in that pit that you the retention basin. I guess that's.
Yeah, of course, if you implement this in a real situation, you will also need to add some drainage to this retention facility. Yeah.
Yes, of course. Okay. Well, thank you all for listening. Leendert, thank you for your demonstration. Very interesting to see all these tools come together in a sort of an example use case. Thank you very much. And with that, well, let's see if I can end the webinar. And I will do it, I guess. Okay, thank you all. Bye-bye.
Thank you.